Welcome back, everybody. Let's work through this group work on partial derivatives and the chain rule. So to start, we have our function here of two variables, and x is a function of st and u. Y is also a function of st and u, and we're wanting to find the partial of f with respect to s using the chain rule. And so here, once we know the variable we're differentiating with respect to, it all comes just from the structure of the function and then adding up all the paths to that parameter in this case. All right, so to start, we have our function f of two variables, and each of these is in terms of the parameters st and u. And we have these two paths down to our parameter s. And so adding those up, we get our formula for the chain rule. So del f del s is going to be fx for the first bar on the left times xs plus fy for the first bar on the right, and then times ys. So we have just these four partials to compute, and then we can just pop them where they go. And here we want to figure out what value we're actually getting when we plug in 4, 2, and 1 for st and u. All right, so for fx and fy, we just look at our original function and take those partials. So with respect to x, we're going to get 4x cubed plus 2xy, and leave a little space. With respect to y, our original function's partial just gives us the x squared, because the x to the fourth goes away. And now for xs, we're now just looking at our formula for x, and if we're taking the partial with respect to s, then our other variables t and u are constant, and so in the derivative those just go away, and our derivative with respect to s is going to be 1. For the last piece here, y with respect to s, we're just looking at the formula for y, and if we're taking the derivative with respect to s, then t and u are constants, and so this tu squared is just some ugly constant multiplied against s, so in the derivative the s just goes away, and we're left with tu squared. And so there's our formula. We could plug in for x and y in terms of st and u if we want, but it gets pretty ugly. I like just leaving it like this. And we can plug in 4, 2, and 1 for st and u, and where we see x and y, we can plug in using the formulas that we have. So here, x is going to be s plus 2t minus u, so 4 plus 2 times 2 minus 1, which is 7, and y, coming from our formula stu squared, becomes 4 times 2 times 1 squared, which is 8. So here we can take these values and feed them in. So at our point, I'll say, just so I don't have to write all those values for stu, x, and y, we get 4 times 7 cubed plus 2 times 7 times 8, and times 1. I'll write it in just so we can see we thought about it. Plus x squared, and then times tu squared, so t is 2, and then times 1 squared. And if we crank that into our calculator, we're left with a value of 1582. Pretty big, but that's just what it is. Essentially, we just are getting a fast rate of change from our function as we are increasing our parameter s at this value, our function is increasing very rapidly at that point in that direction. All right, let's look at our next one. So here we actually have a contour plot for a function f, and we're wanting to estimate its partial derivatives at 2, 1. And so here, let's find our point. There we are at 2, 1. And so the way that we can think about this is by analogy. Back in Calc 1, right, we would, that's a terrible picture, there we go, something like this. If we wanted to estimate, say, a function's derivative over a value at, I don't know, if it's at like 4 or something like that. Well, the one way to do that, just in a very basic way, is to just take a step out, maybe to 5, come up, get a second point, and then just connect the dots and say that the slope of the tangent, the true tangent slope, should be approximately, just the change in y over change in x there, just the slope of that secant line. Right, and we could also, we could bounce back in the other way as well, and get another slope over on this side, and we could kind of take the average to get some sort of reasonable, better estimate for our true tangent slope at our point 4. And so this is what we're keeping in mind. Here, if we're taking the partial with respect to x from this point, right, we're just wanting to step out in the x direction. And so here we could step out a little bit 1 in the x direction, but here we just have to read our contour plot correctly, right? We're kind of imagining we're taking a walk up on a hill, and so the elevation values, the z values, are coming from these labels here on the contour line. So here, for this step out, we started at z equals 10, and we stopped at z equals 14. And so we moved up from 10 to 14. And so here, fx, our estimates here, this first step, we had a change in, I'll kind of do it like this. So f of x is approximately the change in z over change in x that we saw. The change in z, we went up from 10 to 14, so I'll write this as 14 minus 10. And our change in x, right, was 1. I'll write it as 3 minus 2. All right, and that gives us 4 over 1, which is 4. Now if we take a step backwards, and I don't know, it's a little bit fuzzy, but here now our z value is, if we want to be kind of imprecise, which I do in this moment, we could just say that z value looks like about 8. We could do 7.8 or something like that if we wanted to be a little bit more accurate. But still just a change in x in this case of depends on which direction we want to think of this, but essentially if we were moving out to the left, it's a change in x of -1, and so we can write this like this. So change in z, change in x. All right, so our z2 we said was 8. Subtract our original, which was 10. Our new x is 1. Our old x was 2. And so we get -2 over -1, which is 2. And if we now kind of just do a quick sanity check here, the fact that we have +2 is good, right? Because we started here and moving to the right, we're moving uphill up to the value of 10 from our value of 8. So we should have a positive slope. So that looks good. And then here, if we want to take the average here, we can say fx is about 4 plus 2 over 2, which is approximately 3. And that'll be good enough for us. Now, if we want to play this similar game for approximating fy, now just instead of moving in the x direction, we're going to be moving in the y direction. And so here, if we come up in the positive y direction from our point, and I'll kind of make a fat point, and so we'll say that there we got the z value 8, and down here we have the z value 10, right? So we expect a negative slope. So the change in z over change in y, that's going to be 8 minus our original, which was 10, over our new z value is 2, old one was 1, and so a slope of -2 is what we're getting. And here if we step backwards down to the x-axis and look at our change in z over change in y, our new z is 12, our old one was 10, so we have 12 minus 10 divided by our new y was 0 minus our old y of 1, so we get 2 over -1, which is -2. And averaging those together is just going to give us -2 again. Okay, we could have done a little bit better if we hadn't been so rough with our estimation. Maybe this is like 7.5 or something like that, but we just kind of rounded it to 8. All right, this next question is asking about this parametrized curve that we can see in the graph. We can see that we're kind of moving this direction, and again the idea here is that we are on top of this hillside, and this is kind of showing us our hiking path as we move along this hill. And we're wanting to find these points where df dt is 0. So df dt, right, informally, is the slope of our feet as we walk along this path. More precisely, it is the rate of change of elevation as we move along this path at each point in time. And so if we're wanting to find where this value is 0, we're wanting to find where our rate of change is 0, or our slope of our feet for just an instant is 0. So our feet are horizontal. And so if you kind of imagine kind of what this would feel like to walk along this path, maybe if we start here at this value of 8, notice as we walk along this path, we're moving up to this elevation of 10. And so along that side, we're always walking uphill, right? So our feet are always pointed up and not horizontal. And after we get to 10, we're going a little bit higher up on our hillside, but at a certain point, maybe right about here, we're going to be turning around. And right at that moment where we turn around and stop going uphill and start going downhill, then that's going to be where our df dt is 0, right? The slope of our feet will be 0 for an instant. As we continue on this path, now we're starting to go downhill, right? Down to elevation of 10, 9, 8.5, and actually here, right when we get to the elevation of 8, right, that's the lowest we get, and so that's when we start going uphill again. That's when we're turning around, and so there's another turnaround point. So those looks like be the only 2 points where our feet are going to have horizontal slope, right, where the rate of change of elevation is 0. Notice here on the left, what's kind of special about this point is that it is tangent to this level curve. And indeed, if we could somehow visualize, you know, like the level curve that went through this point, it would be tangent to our curve there, right? Because you can think of it, when you turn around, well, you've reached your maximum height, you're going to be going back downhill now. And so we got those 2 points, and so yeah, just asked us to mark them on the graph, and so it looks like we're done. We're turning around here and here, right? That's where our df dt is 0. go down to our next question. We have some surface in three-dimensional space defined by this equation, and we're wanting to find these partials, giving us the formulas for the slope on the surface in these two different directions. So the first thing we have to do is remember our derivation of our formula for del z, del x, and del z, del y, right? That looks like negative fy over fz for that one, and for del z, del x, it's going to be negative fx over fz. That used the fact that our equation looked like f equals some constant, where here our equation doesn't have that. It's got our variable stuff on both sides. So what we want to do is just pick a side and toss all of our variables over. And so if we do that here, we get 2 e to the z minus cosine of x, y, z equals 3. And now all this stuff on the left, that's our f from our formula. And so this is the thing that we can just take the partials of and put in these formulas where they go. So here we go. Del z, del x is going to be negative fx over fz. So taking the partial of this thing, our green box function with respect to x, the first piece just goes away because y and z are constant. And over here, we have a little chain rule to work through. So we have a negative cosine. The derivative of our outside function is going to be negative cosine, so those negatives will cancel out. And maybe I'll write it in though. So we have the negative sine evaluated inside x, y, z, and then times the derivative over inside with respect to x is going to be yz. On the bottom, our f with respect to z. Now we do catch this first piece and the second, but x and y are constants in this case. So we're going to get just 2 e to the z plus, because I have double negative, sine of x, y, z, then times the derivative over inside with respect to z, which will give us x, y. And so up top, right, those two negatives will turn into a big plus, but we still have the negative there. And so it'll be a negative sign upstairs, and then the green stuff downstairs. Our other computation for del z, del y goes similarly. Now we're upstairs taking minus the partial of f with respect to y. And so once again, the first piece goes away because z is a constant. And we've got a chain rule here. Again, it's going to be a positive sign because of the double negative, x, y, z, and then times the inside as derivative with respect to y, which is x, z. And then down below, f with respect to z is still the same. So we can just copy paste from our computation before. And there we go. If we had a point x, y, z on the surface, we could feed it into either one of these equations, and it would tell us the slope in the positive x or positive y direction. Next one here, we have a figure out which is which. It says one of the following graphs is a function of two variables, and the other is its partials. So let's figure out what's going on here. And so there's definitely different ways to kind of play around with this. One of the things we want to recognize right off the bat, though, is how these graphs are working. Notice here on the side of the graph, we have the label x, and it starts negative here and moves positive as we move towards us. And so the idea is that the x-axis is kind of at least would actually go through the center of this cube, but the positive extraction is kind of this way, kind of out and to the left, or towards us and to the left. With that in mind, let's pick a point and kind of analyze what's going on here. If we pick, let's say, this point on our graph, and look in the positive x direction, we're going downhill, right? So the slope would be negative. So if this were the function, then we'd expect the partial with respect to x to be negative here, but actually, if we look at the kind of same spot, corresponding spot in these two graphs, the value is positive and positive. So neither one of these functions could be the partial with respect to x of this thing, and so this first graph is not the function. If we play a similar game here and kind of pick maybe a point on this kind of corner facing us, and again look at the slope in the positive x direction, this time we're kind of moving uphill as we move in the positive x, and so here our slope is going to be positive in the x direction. And if that's true, then looking at our two other graphs, this function wouldn't be its partial with respect to x because that value is negative there. But over here, this could work out. But let's see, how could we check to see what's going on? If this were the function, then this partial would be with respect to x. So we're saying here, is this the function? If it is, then this would be the partial with respect to x, and this is the partial with respect to y. And so we can just kind of test this out. And let's see, if we look at the partial with respect to x, let's see, does this work everywhere? Over here, the partial in the x direction would be negative. It'd be negative the whole way through. That's kind of what I'm seeing. If we look at these other points, negative, 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 negative. Sorry, it took me a minute to kind of see how I was going to feel this out. Right, those are all negative in the x direction. But if we look here at this graph, if we're saying this might be the partial with respect to x, if we look at these values, they're negative, but they're coming up and they actually look like they become 0 here. And so that's not what's happening with those points here. And so right there, we can say, okay, that can't actually be the partial, this can't be the function, and so that's not fy. And so by process of elimination, this graph over here must be the function. And let's play our game, right? Moving in the positive x direction. See if we could kind of pick a point here, close to the corner. In the positive x direction, we're moving up. And so whatever fx is, we should have a positive value there, our second graph, the value of this graph is positive, whereas here the value of the graph is negative, and so this has to be our with respect to x, and this has to be with respect to y. Different ways you can feel it out, but essentially just kind of pick a point, think about what's going on, and see if the other graphs are matching what's going on. All right, one more. So here we have a function of two variables, and g of rs is just a composition of that function with some other parameter formulas. And so this looks kind of goofy, but essentially what we're being told here is the structure of our function, that our function f is in terms of two variables, and x is in terms of two parameters, r and s, and same for y. And we're wanting to compute the partial of g with respect to r and g with respect to s at the points 1, 2. And so here, again, it's a little bit goofy, but this g function is just our composition here. All right, and so we're taking the partial of our composition with respect to, in this case, the parameter r to start. And so using the chain rule, we just need to add up the two paths to our parameter, and we'll get our formula, and we can see how to use the information we're given to do that. So, f with respect to r is, on the first path, fx times xr, and the second path, fy times yr, and so the partial of f with respect to x at our, let's see, I'm looking over here at the table, we're given some f information. We don't know what f actually is, right? So we kind of need to rely on this, what's over here. We have fx, but at two different points, and so these we need to interpret. So we have r equal to 1 and s equal to 2, and if we use our formulas, we can figure out what's going on for x is going to be 2r minus s, which is going to be 2 times 1 minus 2, so that's 0. And y is going to be s squared minus 4r, and so that is 2 squared minus 4 times 1, and so that is 0. So the xy that we are talking about here is 0, 0. And since those are the variables for our function f, that's what we want to use to compute fx. So it looks like our value of fx at 0, 0 is 4. And similarly, fy we can grab at 0, 0 and see that that's 8. These other ones, x with respect to r. So here, we don't have any x information on our table, but we actually know the formula for x, right? Since x is 2r minus s, xr is just 2. Feed that in. And then similarly, y with respect to r, we don't have any y information in our table, but we have y information in the statement. So y is s squared minus 4r, so yr is negative 4, and we can feed that in. And just computing, we get negative 24. Similarly, for our other partial with respect to s, now we're just going down the paths, the two paths to s. And so our chain rule formula becomes fx times xs plus fy times ys. And once again, we can just find this information and feed it in. We're still evaluating at r and s being 1 and 2, and so x and y are still 0, 0, and so our fx and fy values from before are the same, 4 and 8. But now x with respect to s is our partial that we need to find, and just using our formula for x here, it's going to be -1. And then y with respect to s, using our formula, is going to be 2s. And right at the point that we're looking at, s is 2. And so just cranking that out, we get the value of 28. Great work, everybody. I'll see you next time.